Mankind has seen very little evidence of extraterrestrial life beyond Earth. So far, we've only been able to map out exoplanets possibly capable of supporting life, none of which has yielded any form of intelligent life. But that all changed when scientists intercepted a signal from space originating from the region of Proxima Centauri, the closest star to our solar system. The discovery of this signal changed the possibility of extraterrestrial life beyond Earth. But where and how did this radio signal come from, and what have scientists concluded to be the possible source? To find that out and more, stick with us as we run through the mysterious signal from Proxima Centauri. Proxima Centauri is by far the most interesting star system studied by scientists here on Earth. Being the closest stellar neighbor to our Sun, located just 4.2 light-years away, this star is much smaller in size and mass and sits in the southern constellation of Centaurus. Discovered way back in 1915 by Robert Inner, Proxima Centauri isn't visible to the naked eye with a quiescent magnitude of just 11.1 and can only be observed via telescope. Much like our solar system, Proxima Centauri has stellar bodies which have been identified as exoplanets orbiting it. With a mass of roughly 12.5% that of our Sun's, Proxima Centauri is a dwarf star with a much larger average density, about 33 times that of the Sun. This means the star is much heavier and exerts a stronger gravitational pull on the stellar bodies that orbit around it. And although Proxima Centauri has a very low luminosity, it is categorized as a flare star which randomly and quite violently releases solar flares packed with high levels of radiation. These flares impact the two known exoplanets that orbit the dwarf star, Proxima Centauri b and Proxima Centauri d. There is another candidate exoplanet, Proxima Centauri c, orbiting around 220 million kilometers from the dwarf star, completing one orbit once every 5.2 years. But due to its apparent distance from the star, the existence of Proxima Centauri d is still heavily debated by astronomers around the world. The existence of the other two planets has been confirmed and is currently being studied by astronomers and scientists. Proxima Centauri b orbits the dwarf star at a distance of 7.5 million kilometers, completing a full rotation in just 11 Earth days. It is fairly similar to Earth with a mass of just 1.17 times that of Earth and rotates within the habitable zone of Proxima Centauri. At this range, it is possible for atmospheric formation, and temperatures are just right for the formation of liquid water on the surface of the exoplanet. But this has been highly debated by scientists, as Proxima Centauri is a flare star and randomly releases bouts of electromagnetic radiation and solar flares that would make habitability on Proxima Centauri b highly unlikely. Proxima Centauri b receives about 10 and up to 50 times as much radiation on its surface as we do here on Earth. High levels of radiation on Proxima Centauri b could lead to increased levels of oxygen and carbon monoxide, which may build up in whatever atmosphere the planet has. But these high oxygen levels may lead to the evolution of complex chemicals and organisms which could possibly account for organic life on the planet. This idea has been floated around by scientists who believe Proxima Centauri b might have an entire atmosphere filled with organisms, which could possibly be the reason and source behind the signal which recently emanated from the region. The possibility of water on the exoplanet could also lead to chemical reactions which could be conducive to the development of life and as such may cradle some form of extraterrestrial species, all of which still remain theories at this stage. However, the planet still possesses certain properties that could make it a possible Earth-like planet and is the only planet within proximity to Earth outside our solar system that could be studied for interplanetary travel. Although it will take any current rovers or satellites we have thousands of years to reach the planet, it still holds promise for life outside of our solar system. But although space vessels may not reach Proxima Centauri b anytime soon, scientists studying the region with telescopes here on Earth recently discovered a signal that could only be described to have emanated from intelligent life. In April of 2019, a radio signal was detected and believed to have originated from the region of Proxima Centauri. The signal, which has since been named Breakthrough Listen Candidate 1 or BLC-1, was detected as a result of the Breakthrough Listen Project, which is an initiative set up to search for intelligent extraterrestrial communication throughout the universe. The project has received over $100 million in funding and has dedicated thousands of hours of telescope watch time in state-of-the-art facilities across the planet. Beginning in January 2016, the program still remains the most comprehensive search for extraterrestrial communication outside of our solar system. The signal or techno-signature was picked up by the CSIRO Parkes Radio Telescope in New South Wales, Australia. At the time of the discovery, the telescope was observing the region of the closest star to our Sun, Proxima Centauri, which it had done hundreds of times before. Over time, the telescope picked up vast amounts of data, and scientists didn't pick up the signal right away. At the end of each observation cycle, they had to filter through hundreds of thousands, sometimes millions of signals to single out any unique techno-signals which might originate from space. And to give you a sense of what they are looking for, the signals must have two distinct properties. The first was that it must be confined to a very narrow broad band of frequencies, much similar to radio broadcast on Earth. This is unique because no natural process is able to produce this kind of signal, and it will definitely raise red flags if it were to originate from space. The second property is that the frequency of the signal must drift in a way that is similar to the motion of exoplanets relative to Earth. During this particular observation cycle, the telescope in Australia picked up over 4 million distinct signals, and the team had to get to work filtering out unimportant signals and leaving out the rest. The team was able to filter out much of the background signals that originated from Earth and were left with over 5,000 distinct signals. The team then had to further cross-check these signals with radio transmitters currently on Earth and were finally left with a single, unexplained signal. The team of scientists described the signal as a unique techno-signature with a narrow broadband that appeared over a 30-hour observation period and only when the telescope was pointed towards Proxima Centauri. The discovery of BLC-1 indicated that it possibly originated from Proxima Centauri and had a distinct feature to the WOW signal discovered back in 1977. The WOW signal was a strong narrowband radio signal discovered by Ohio State's Big Ear Radio Telescope, which was the premier tool used in the search for extraterrestrial intelligence. The WOW signal appeared to have originated from the constellation Sagittarius and was the first sign of extraterrestrial communications outside our solar system. The signal lasted for about a 72-second window and has since not been detected by any other telescope anywhere else in the world. There have been several hypotheses to the origins of the WOW signal, including human-made sources, none of which have adequately explained the signal's origins. It currently remains the strongest possible evidence for a radio-transmitting extraterrestrial civilization outside the solar system. But although BLC-1 had similar properties to the WOW signal, scientists at the Parkes telescope needed to ensure they had eliminated every other possibility that could explain the origins of the signal. This was paramount because attributing a radio signal to extraterrestrial civilizations was to be made as a last resort when no other possible hypothesis could account for the signal's origins without a doubt. To this end, a remarkable level of investigation was put into eliminating any conventional explanations for the signal's origins. First, the team began observing Proxima Centauri almost 2 years after the initial signal was detected in an attempt to replicate the initial observation conditions which led to the discovery of BLC-1. The team has been unable to locate any evidence of a signal similar to BLC-1 in the Proxima Centauri region. The team then went on to investigate the possibility of a moving transmitter which could explain the source of the signal. This included moving objects such as trains, planes, helicopters, balloons, and any other electronic device capable of transmitting signals long range. However plausible this angle of investigation was, a moving transmitting object could not sufficiently explain the fact that BLC-1 appeared constantly over several hours. The team came to the conclusion that a moving transmitter could not possibly explain the trajectory which produced the drift of BLC-1 for such a long period of time. In a statement to the press, the team stated that it is extremely difficult to construct a continual motion path that could persist as exhibited by the measured signal, even by varying the speed along the route. The team also came to a similar conclusion when investigating satellites as possible explanations for the origins of BLC-1. This is because satellites in low Earth orbit move too quickly to produce signal drifts for such long periods, and geostationary satellites do not drift at all. it was concluded that no satellite in orbit could have possibly produced BLC-1. Then the team moved on to investigate deep space probes such as Voyager 1 and 2 as possible origins of the signal, with the probes being the only man-made signal-transmitting objects in deep space. But the team was also able to rule out these probes as none of them were in line with the telescope or remotely within any region close to Proxima Centauri. The team finally decided to study the signal itself, which they then noticed had an apparent shift consistent with the Doppler effect. This in turn suggested that the frequency itself was inconsistent with what could have been caused by movement on Proxima b or any planets orbiting Proxima Centauri. The signal itself had a frequency of 982.002 MHz and having a Doppler shift that increased in frequency rather than decrease. This prompted the team to look at drifting signals similar to BLC-1 in the previous data, which had been discarded earlier on in investigations. Surprisingly, they found 5 similar signals to BLC-1, and after looking further, found 27 other mirror signals of BLC-1, and it was at this point the signal's origins became clear. The signal frequencies were multiples produced by interactions of common clocks and other digital electronic devices. Apparently, the Parkes telescope was picking up on its own radio frequency interference, although an albeit rare and minute form of it. The complexities of BLC-1 just go to show the intricacies involved with searching for extraterrestrial communication in the universe and have served as a checklist for future signal discoveries. Do you think we'll ever discover any extraterrestrial communications in our lifetime? Let us know in the comments. We'll see you in the next video.